So this next video, we are diving into exponents, moving on from division a little bit, but we will come back to it slightly at the end of this video. So exponents, the numbers that we use are place values. They're all named according to what we call powers of 10. Powers of 10. What do we mean by that? A power of 10. What you see here, when we write 10 with an exponent of 1, that's called the first power of 10. And it is just stating the number 10, like you see here. If we put an exponent of 2, that's the second power of 10, which is 100. We can continue on. The third power of 10 is 1,000. Those exponents are telling us how many times we're multiplying this base number by itself. 10 times 10 is 100. 10 times 10 times 10 a third time is 1,000. And notice also our number system, right? We have names for the first, second, and third powers of 10, 10, 100, 1,000. After that, we just start repeating them, and every third gets its own name: million, billion, trillion, right? So the process of using exponents, the operation, if you will, of raising numbers to a power is called exponentiation. Exponentiation. Again, that is the operation of raising numbers to a power. And of course, we have a nice formal definition, which we all love. And that's what this is, our formal definition of exponentiation. So again, I recommend pausing and trying to make sense of this first, and then coming back and listening to my explanation. So exponentiation, for any number b and the whole number n, with b and n not both 0, one can be 0, but not both of them, we say this: b to the n power, b to the n, is equal to b times b times b times b times b, n number of times, right? So it's repeated multiplication. That's the key. Exponents imply repeated multiplication. B is called the base, right? So the number below is called the base, and n up here is called the exponent, right? So we have a base and an exponent, and the process is called exponentiation. Okay, so the exponent tells us how many b's are being multiplied. Now, there are a couple special situations. In the case where n is equal to 0, meaning your exponent is 0, b to the 0 power is equal to 1. Any number with an exponent of 0 is equal to 1. And if n is equal to 1, so your exponent is 1, b to the first power is just b. So it gives the same number back. Okay. So we're going to try some of these where we evaluate expressions involving exponents. So the first one is, again, we will evaluate. When we use the word evaluate, it means find the value of. Values right in the middle. Find the value of. 3 to the 4th power. So if we want to evaluate that, it tells us that we have to take the base is 3, and we multiply it by itself, the exponent number of times. 3 times 3 times 3 times 3. And if we multiply those all out, we get 81. You'll see 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is equal to 81. So go ahead and try these next 3 on your own. 2 to the 5th, 5 to the 0, and 6 to the 1. So for the first one, 2 times 2 times 2 times 2 times another 2. So 5 2's all multiplied together. So we have 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 2 to the 5th power is equal to 32. 5 to the 0 power. Do you recall from a moment ago, we said any number, any base with an exponent of 0 is always equal to 1. It's always going to be just the number 1. It doesn't matter what the base is. It will always be 1. And then finally, 6 to the 1st power. If you have an exponent of 1, then it's just going to be the base. So some more terminology that we have. A number written in the form b to the n is said to be written in exponential form. All right. So when we write a number in exponential form, or b to the n, it's said to be in exponential form. An example is 32 moments ago. That was the answer to 2 to the 5th. So this is our number, but this is exponential form right there, 2 to the 5th power. Sometimes it's beneficial to us in certain situations to write a number in exponential form. Another phrase or term to go along with that is, we say that in general, the number b to the n is called the nth power of b. Okay, so we would say this right here is the 5th power of 2. Okay, so even we could say 32 is the 5th power of 2, right? And it's written in exponential form like this. So this is just some of the language that we often use in mathematics. The 5th power of the base 2. Now we have special names for a couple of these as well. So if our base is b, then when we have b with an exponent of 2, right, the 2nd power of 2, we often say that is b squared. B squared. If we write the 3rd power of b, we call that b cubed. And that terminology really came from the ancient Greeks, because the Greeks viewed all of mathematics and numbers as associated with geometry, pictures. They had pictures for everything. And so they envisioned these as geometric arrays of dots. And so you can see from this figure right here, 2 to the 2nd power. If we look at it, this image on the left here, which is a square, 2 times 2 is 2 to the 2nd power, right? You have 2 times 2, 1, 2, 3, 4. So they would say that 4 is what we call a square number. Okay, this shows 2 times 2, 2 this way, 2 this way, and it actually makes something that looks like a square. Similarly, 2 times 2 times 2 is 2 to the 3rd power. We see we have 2 times 2 here with our length and our width, but then it also has depth to it, right? So we have that 3rd dimension. And so 2 times 2 times 2 is 8. Count how many of those dots are there. 1, 2, 3, 4, 5, 6, 7, 8. So we say 2 to the 3rd power is a cube number, or 2 cubed, because the number of dots can be arranged physically in an actual cube. All right, so cubed and squared are numbers, are words that we use quite a bit. Now, any number, if that's greater than or equal to 1, if we can write it as a second power, then we call it a perfect square or a square number. So here's what I mean by that. If we take 1 squared, we get 1. If we take 2 squared, we get 2. 3 squared is 3. I'm sorry, I messed that up. Let me fix that. I apologize. Let's erase those. 2 squared is 4. Thank you. 3 squared is 9. 4 squared is equal to 16. And we could continue that pattern forever. These numbers, these whole numbers, 1, 4, 9, 16, and so on, are called square numbers, or I prefer perfect squares. They're called perfect squares. And the reason is they can be arranged in a square. The number 4 we just saw, 1, 2, 3, 4 is a square. So can 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 3 by 3 makes 9. Any numbers, if we continue this, 1, 4, 9, 16, what would be the next perfect square? 5 times 5 is 25. Next would be 6 times 6, which is 36. Those can all be arranged in a square. Similarly, if we take things to the third power, 1 to the third power is 1. 2 to the third power is 8. 2 times 2 times 2. 3 to the third power is 27. 4 to the third power is 64. These numbers, maybe you can even guess, the result from cubing a number, these are called perfect cubes. And they could all be arranged in physical cubes of dots like we saw above. Now, multiplication and division can be performed pretty easily with numbers that are written as powers of the same base. So if we are multiplying 2 powers that have the same base, or dividing 2 powers of the same base, that can be done fairly easy with what we call one of the laws of exponents. And I'm going to write this up here, and then we're going to make sense of it. So let's explore this formal definition. For any number A, all whole numbers m and n, except for the case where the base and exponents are both 0. So if they're both 0, we're not considering that. So A and all whole numbers m and n. Let's first take a look at this top one. A to the n times a to the m is equal to a to the n plus m. Let me write that bigger. So what is happening here, what you're seeing here is if you have a base of 5 and an exponent of 2, and another number that has a base of 5 and an exponent of, say, 4, and we need to multiply those 2 numbers together, we can do so by combining them into just one single base, only stating the base once, and adding the 2 exponents together. This would be equal to 5 to the 6th. Now, why does that work? It's because 5 to the 2nd is really 5 times 5. And 5 to the 4th is 5 times 5 times 5 times 5. And all we're doing is we are multiplying those 2 expressions together. So what's the total number of 5s that are all multiplied there? There are 6 of them, 5 to the 6th. So when we're multiplying numbers and they have to have the same base, we can just add the 2 exponents. Keep the base the same, add the 2 exponents. if we are dividing a to the n divided by a to the m, then we're going to subtract a to the n minus m. Okay, so that might look like 10 to the 7th divided by 10 to the 3rd. That would be equal to 10 to the 7 minus 3, which is 10 to the 4th. So this division can be done by just subtracting the exponents to get a new single exponent. Why does that work? One of the reasons is if you think about division in terms of a fraction, and we will see this more in a moment, 10 to the 7th can be written as 10 times 10. Should have picked a smaller number. 3, 4, 5, 6, 7. And we're going to divide that by 10 to the 3rd, which is 10 times 10 times 10. What's going to happen here is 3 of these 10s are going to divide out to just be a single 1. 10 divided by 10 is 1. Another 10 divided by 10 is 1. Another 10 divided by 10 is 1. And often we say they're just going to cancel. What are we left with? We're just left with those 4, right? We started with 7 on the top, the 3 on the bottom, canceled out with 3 on the top, leaving us with just 4. So try a couple of these on your own. Let's see. Let's do. Oops. So let's do 2 to the 4th divided by 2 to the 3rd. And then let's also do 2 to the 8th. I'm sorry, that was wrong. I wanted to do times. Sorry, 2 to the 4th times 2 to the 3rd and 2 to the 8th divided by 2 to the 3rd. So go ahead and pause, take a moment, and see if you can evaluate those and do 2 things. State them in exponential notation and then actually evaluate them and give their real value. For that first one, 2 to the 4th times 2 to the 3rd, we know that we are going to be adding those 2 exponents, which is 2 to the 7th. If you actually multiply 2 to the 7th out, you get 128. And again, the reason why this works is because of this. If you think about what 2 to the 4th times 2 to the 3rd means and wrote them expanded, they mean this. 2 to the 4th, 2 to the 3rd ends up to be a total of 7 2s all multiplied together, which is then 128. For this one, 2 to the 8th divided by 2 to the 3rd, we're going to be subtracting 8 minus 3, which is equal to 2 to the 5th. And if we multiply all those out, I actually saw this one earlier, that is 32. Again, why does that work? Let's take a quick look. It works because of this. Again, like we showed before with the division, 2 to the 8th goes on top, 2 to the 3rd goes on the bottom, and you end up with 3 2s canceling out, which is like subtracting them, and you're left with 2 to the 5th. Multiply that out to get 100, multiply that out to get 32. Just a final example of these. Consider this, these questions, all right? We got 3 questions that are all connected to each other. This is kind of fun. So in our galaxy, there are 10 to the 11th, or 100 billion stars. And in the observable universe, there are 10 to the 9th, or 1 billion galaxies. If every galaxy had as many stars as ours, there would be 10 to the 9th times 10 to the 11th stars. So write that product in exponential form. Go ahead and pause, reread and pause that if you need to. Then go ahead and do that. So what we're doing here is we're multiplying 10 to the 9th times 10 to the 11th, which gives us 10 to the, what are we going to do? Add those exponents. Again, the bases are the same. They're both 10. So we can add them to get 10 to the 20th power. Okay? So again, there would be, if every single galaxy that we know, that we can see, right? Every single galaxy had as many stars as ours does, Milky Way, then there would be 10 to the 20th number of stars that just exist. Okay, so that's the first question. The next question is this. We're going to extend that one. If one, let me just literally extend this writing here. If one out of every 1,000 stars, out of these stars that we just calculated, if one out of every 1,000 had a planetary system, like we have around our sun, there would be 10 to the 20th divided by 10 to the third stars that have planetary systems. So write this quotient in exponential form. Again, take a moment to pause, reread that, and do that last step. So in here, we would be taking 10 to the 20th from our previous question, dividing it by 1,000. And notice how we rewrote 1,000 in its exponential form, 10 to the third. What do we do there to do that calculation and keep it in exponential form? Subtract 20 minus 3, which is 10 to the 17th power. And then we have one final question. And it is this. If one out of every 1,000 stars with a planetary system, so again, remember, these have planetary systems. If one out of every 1,000 of these had a planet, a singular planet with conditions that are suitable for life, there would be 10 to the 17th divided by 10 to the third such stars. Again, there's that 1,000 written in its exponential power or exponential form. There would be that many stars. Write this quotient in exponential form. So again, reread that one, make sense of it, and then do that last step. So again, 10 to the 17th divided by 10 to the third is 10 to the 14th. 10 to the 14th power. So that's a fun little question, problem, a series of questions, all using a base of 10 with certain exponents to kind of throw out some probabilities of possible planets that exist out there that could be sustainable for life. That's a pretty big number if you multiply all those out. So the very last thing we're going to talk about in this video is we're going to go back to order of operations. We talked about this a little bit. In a previous video. It's not what I wanted to do there. Order of operations. There we go. Order of operations. And so we talked about this in section 3.3, but we're going to extend it now to include division and raising numbers to powers. So the order of operations requires that, I'm going to just state these in a list here. And then we'll explore them and consider things you already know about this. So the order of operations suggests that numbers that are raised to a power should be evaluated first. Products and quotients are computed in the order in which they occur from left to right. So that's multiplication and division. Sums and differences, adding and subtracting, are calculated in the order in which they occur from left to right. So we do powers first, or exponents. Then we take care of our products and quotients, and then we do our sums and differences. Now, there's an exception to the rule. An exception occurs when operations are written with a grouping symbol, such as parentheses, like that. And in this case, those computations within the parentheses are carried out first. Now, you've probably learned an acronym like PEMDAS. Please excuse my dear Aunt Sally to help you remember this. I'm just going to modify this a little bit for a couple of reasons. One is PEMDAS implies that M comes before D. And we just read in this statement here that those occur from left to right. So I prefer to write not M on top of D, but I like to write them right next to each other. The same thing occurs with these two, A and S, adding and subtracting. We know that addition does not have to come before subtraction. So we often can just write them as A and S next to each other like that. You do them from left to right. Exponents do come before these two, but I don't even like a P for parentheses. And the reason is there are lots of symbols in mathematics that are grouping symbols. And so I prefer a G for grouping symbol. There could be parentheses. You can have brackets that group things together. Even a fraction bar has multiple things to do on top and multiple things to do on bottom. So there are implied groupings on the tops and bottoms. Square root symbols can group things on the inside. So there are many different grouping symbols other than just parentheses. So let's take a look at how these might work. So the first one we'll look at is 4 times 16 plus 16 divided by 2 to the 4th. So what I want you to do here is just follow along with me on this one, and then we'll give you several to try on your own. So I'm going to go off to the side. I'm going to write grouping, exponents, multiply, divide, add and subtract. This is like a checklist for as I go through this one. The first thing I'll do is check to see if there are any grouping symbols. There are not. I have no parentheses or any such symbol. So we have taken care of that. Do we have any exponents? Yes. So this part of our expression must be evaluated first. 2 to the 4th power is equal to 16. So I rewrite, the way we do this is we rewrite the entire expression from left to right, only replacing the calculation that we just evaluated, 16. There are no more exponents in our problem, so we proceed to the multiplication and division. Now I see 2 of them, one here and one here. We are going to do them from left to right. So first I will do 4 times 16, which is equal to 64, plus, and then I will do this one, 16 divided by 16, which is 1. I've now completed my multiplication and division, so I can proceed to my addition and subtraction, of which there is just 1, and we end up with 65. So that's the order in which we need to do these operations when you have more than one thing to do in a problem. So let's give you several of these to work out on your own. So the first one is 4 times, in parentheses, 6 plus 16, then divided by 2 to the 3rd power. The second one is 220 minus 12 times 7 plus 15 divided by 3. And the third one is 24 divided by 4 times 2 plus 15. So pause, try these on your own. So, how did you do? And when you're first learning these or trying to improve on these, I recommend that when you do it, you write out your little checklist. G, E, M, D, A, S. And check them off as you go. So for this first one, we would look for our grouping symbols. We have parentheses, so we would have to start with that. So 4 times 6 plus 16 is 22, and then divided by 2 to the 3rd. Next, we have exponents. exponents. So I will do 4 times. Now, I left my 22 in parentheses. You could have removed those parentheses at this point if you would like. I will go ahead and do so. They're not grouping anything anymore, so we can remove them. Divided by 2 to the third is 8. My exponents are done. Now I'll go to my multiplication and division. So I work those from left to right. I have 4 times 22 here, which is 88. I have to bring this division by 8 down because it's connected to that 88. Now we will do our final division. 88 divided by 8 is 11. Notice how every time I rewrite the problem with one singular calculation done. We had no addition and subtraction, so that's it. Let's go to number 2. G, E, M, D, A, S. So I scan my entire problem. 1, 2, 3. There are 4 different operations here. There are no grouping symbols. There are no exponents, but there is multiplication and division. So I will bring down my 220 minus, I will multiply 12 times 7, which is 84, plus, I can also do this division now, even in the same step, because it's disconnected from the other multiplication. Okay, there's an addition sign here, so I can do that division to get 5. Now I look, and there's only addition and subtraction left, so I need to work this from left to right. 220 minus 84. Ooh, that's one I don't think I can do in my head. So I'm going to write 220 minus 84. I will do a little borrowing. 10 minus 4 is 6. And do a little more borrowing. 11 minus 8 is 3. 1 minus 0 is 1. So that is 136 plus 5. I have one more addition to do. 136 plus 5 is 141. Now, one thing you may have noticed is I did this little calculation off to the side. I wanted to keep my organization of my information up here, right? Keep this all consistent. Do any side work you have to do. Last one. Again, grouping, exponent, multiply, divide, add, subtract. There's no grouping. There's no exponents. There's division and multiplication. And notice how the division comes before the multiplication. That's okay. We work it from left to right. This is 6. Bring down the times 2 plus 15. There's more multiplication to do. 6 times 12, or 6 times 2 is 12. Then add the 15. And now we have 12 plus 15, which is 27. So notice on that one, again, I had to do the division and multiplication as individual steps because they were connected to each other. But we did division ahead of multiplication. Even though PEMDAS has the M before the D, we have to do them from left to right. Now, I want to bring you back to one final thing. Way back at the very beginning, our very first video in this section, I gave you this problem. It was an opener, something to consider, and you may have even forgotten about it. If you have your paper where you did those, go and find that. Again, it said using 4 fours and the operations that we know and love, can you write expressions that equal each of the numbers from 1 to 10? The reason I saved it till now is because you actually need to incorporate parentheses and the correct order of operations to do these, to do a lot of them. So here's an example of how you could have come up with the number 1 using 4 fours. You could have done 4 divided by 4 times 4 divided by 4, like that. But notice how my 4s were in parentheses. This is 1 times this is 1. 1 times 1 is equal to 1. There are many other ways that you could have done that. There's just one example. If you're looking for how to make the number 2, you might have done something like this. 4 divided by 4 plus 4 divided by 4. Now, you could have left the parentheses off on that one. It still would have worked because of the order of operations, but sometimes those parentheses are nice just to ensure that your grouping occurs properly. Here's one more. 3 is equal to this. Four plus 4 plus 4 is 12, divided by 4 is 3. But notice how I had to group all those first addition 4s in parentheses. So whatever you did, now maybe you've got some other ideas. Here are some possible solutions that I came up with. They're not the only ones, but again, these are some possible solutions. The slash is another way to write division, kind of like a fraction. So all of these would calculate to be those numbers 1 through 10. Again, the reason I asked you to do that was because it's very connected to order of operations. And now maybe go back and look what you did and rethink to see if any of what you did before might need to be rethought.